This is a trail of newborn stars. Perfectly straight, it stretches thousands of light years across space. When astronomers first found it, they had no idea how it got there and no idea what it was. It was only when they turned their telescopes to the front of the streak that it became clear, and in many ways it's even stranger than the stars themselves. There, leading the charge, is a supermassive black hole racing through space at nearly 1,000 kilometers per second, leaving in its wake millions of newborn stars. But hang on a minute, aren't black holes supposed to destroy stars? How is it that one is creating them? And more importantly, where did it come from? What could have sent this supermassive black hole hurtling through space in the first place? I'm Alex McColgan and you're watching Astrum. Join me as we uncover the spectacularly violent event that's created one of the strangest discoveries in modern astronomy, a runaway black hole. We'll get to the bottom of why this destructive cosmic monster is leaving a trail of millions of stars in its wake, and uncover the truth about how common this strange phenomenon might be. The Hubble Space Telescope has been one of our greatest cosmic tools for decades. We've used it to study starbursts, black holes, beautiful nebulae, and much more. But what it's been particularly useful for is exploring other galaxies. And when a team of Hubble scientists led by Yale University astronomer Peter van Dokkum were looking at a nearby dwarf galaxy in 2023, they noticed something strange, an oddly straight line of young, blue stars and gas. Stretching almost twice the length of our own Milky Way galaxy and containing the mass of roughly 100 million suns, this streak of newborn stars is truly spectacular. And it was a remarkable find. In fact, upon making the observation, Van Dokkum said, "Something like this has never been seen anywhere in the universe." The team quickly got to work attempting to explain this streak of stars, and they came up with several possibilities. Could it be a super thin, edge-on, bulgeless galaxy? Perhaps a runaway black hole? Or even jet-induced star formation? To work it out, they needed more information, and thankfully that was on its way. Follow-up data from the W.M. Keck Observatory in Hawaii revealed that the oldest part of the streak stretched back to a dense, star-forming galaxy about 7.7 billion light-years from Earth. The streak itself was nearly 200,000 light-years long. But these discoveries themselves pose some serious questions. Where did this long, thin band of stars come from? And why did it seem to be forming in the wake of a seemingly massive object? The Discovery team considered all of their potential explanations for the streak of stars, but even with the new data, none of them seemed to fit. The first hypothesis was that this line of stars could be a super thin galaxy, oriented side on to us so we could just see the edge of it. But observations showed that these weren't regular stars. They were all young and blue. A galaxy is usually made of stars that are different ages and colors. Not only that, but the front line of stars gave off an extremely bright signature for doubly ionized oxygen, or O3. This means 2 electrons have been stripped away from each oxygen atom. Making O3 requires very high energy, and it only forms in extreme environments. Yes, galaxies can be extreme, but the chances of it being so at one end like this were minuscule. These observations meant that the culprit likely wasn't a narrow galaxy. The researchers also interrogated the idea that it could be jet-induced star formation from the nearby galaxy. Now, we already have examples of radio jets triggering star formation. We've seen it in Minkowski's object, a peculiar star-forming galaxy near NGC 541, and we've also seen radio-induced star formation in Centaurus A. Perhaps that would explain a straight line of stars. If this were the case, a radio jet from within the nearby galaxy would shock gas in its path, compressing the interstellar gas and increasing its density. This could trigger star formation along the jet's path. And whilst we do see a shock front, more on that later, a simple yet serious problem arises with this explanation: the shape. This feature is narrowest at the tip, the furthest point from the nearby galaxy. In contrast, a jet reaches its widest width at the furthest point. Similarly, the strongest interactions from a jet would be observed closest to the origin of the jet, the galaxy, if this theory was right. Yet, the opposite seems to be true for this unknown feature. The more possibilities the team ruled out, the more they started to wonder whether this streak of stars could have a more extreme, elusive explanation: a runaway black hole. The hunt for answers is not always an easy one, and there was no one to tell these scientists if they got the answer right. The same does not have to be true for our own kids' hunt for knowledge. Classrooms might be hectic, and personal tutors are expensive, but guidance and mentoring are more accessible for our kids than ever thanks to Brilliant, the sponsor of today's video. Brilliant is an online learning platform enhanced with a new artificial tutor called Koji, an interactive mentor who can coach your children on maths or programming subjects without just giving them the answers. I've tried it myself and found that when I told Koji I wasn't sure how to proceed with a question, he offered hints and even drew on my screen to draw attention to things that I might have missed. Honestly, having someone on standby to help me figure out difficult concepts was a lifesaver for me in my university years, and unlike real-life tutors or teachers, Koji is always available to answer when it's needed. See if it's helpful for your kids. Scan my QR code or follow the link in the description below to get started with this Brilliant tutor for free. You can gain access to all Brilliant has to offer by upgrading to Premium, and using my links to do so can get you 20% off your annual subscription. Now, back to runaway black holes. For decades, the idea of a runaway black hole was purely theoretical. In 1983, physicist Michael Fitchett showed that merging black holes could create asymmetric gravitational waves, causing a powerful recoil that could then send the merged black hole shooting off in one direction. Mathematically speaking, these could exist, but no one had ever observed one, and astronomers knew it would be difficult to spot, unless it happened to create a large, visible footprint, that is. The answer came a few years after this streak's initial discovery, when in December of 2025, Van Dockum, once again, led a team of astrophysicists in exploring this space oddity, this time using the James Webb Space Telescope. With its better resolution, the team was able to observe and measure the feature in greater detail. One of the most important pieces of evidence confirmed by the James Webb Space Telescope was that there was an absolutely enormous bow shock at one end of the line of stars. Just as air is compressed in front of a supersonic jet, or a boat pushes through the water and creates a wake behind it, something was pushing on the interstellar medium. Now, obviously, this bow shock is not being created by a plane or a boat. The team thought the most likely culprit was actually a supermassive black hole, at least 10 million times the mass of our Sun, as it plows through space at roughly 1,000 kilometers per second, compressing heated gas in front of it. But they still had to prove it. They were able to measure strong emission lines that confirmed the gas at the very tip of the structure had been heated and compressed by a powerful shock. They also found a sudden jump in gas velocity, indicating that something is moving extremely fast, supersonically in fact, through space. All of this evidence pointed to a single conclusion: the entire structure must be the wake of something absolutely massive. The only thing massive and compact enough to have this effect would be a runaway supermassive black hole. So the team had confirmed the first photographic evidence of a runaway supermassive black hole, and they named it inventively as Runaway Black Hole 1, or RBH1. But there's one problem with this discovery. We typically think of a black hole as the source of a violent destruction, capturing nearby stars and solar systems, even light itself, until it has devoured everything in its path. How is it that this black hole is creating stars? As RBH1 carves a chaotic path through space, its powerful bow shock causes compressed gas to accumulate and trail behind. As it cools and mixes with other surrounding gases, clumps along the trail of gas collapse to form new stars. It is the very chaos of this runaway supermassive black hole that ultimately seeds the distant cosmos with the matter and conditions to form new stars. From cosmic carnage comes stellar rebirth. But why is RBH1 hurtling through intergalactic space at breakneck speeds in the first place? Where did it come from? Luckily, this part of the mystery comes with its own line of evidence, literally. The team led by Van Dokkum said that with the black hole's current velocity of about 954 kilometers per second, the evidence is very strong, bordering on overwhelming, that this is indeed a runaway supermassive black hole that was sent traveling from its once host galaxy. It was flung fast enough to escape its galaxy, and eventually also the circumgalactic medium, the faint halo of gas that surrounds the galaxy. In RBH1's case, the stellar vein leads right back to the source, the cosmic owl. This two-galaxy system is about 7.5 to 9 billion light years away, and it got its name because it looks like an owl with two eyes and a beak. This unique galaxy offers clues to what sent RBH1 on its current trajectory. The shape of this two-galaxy system is very unusual, and was created through the extremely rare collision of two ring galaxies. Ring galaxies make up just 0.01% of all the galaxies we've discovered so far, with only a few hundred known in the local universe. Why? Well, in order to form, they require a galaxy to pass almost directly through the center of another galaxy. As you can imagine, that's not easy. Just like if you're playing darts, chances are much greater that the dart will land off-center no matter how good your aim than directly on the bullseye. And well, galaxies don't come with an innate sense of aim. This means the chance of one ring galaxy being created is already rare. So two of these rare galaxies existing close to each other is even more unusual. Take that one step further, and the chance that two rare ring galaxies collide with each other, well, you can see why the cosmic owl, also dubbed the Infinity Galaxy, is an exceptionally rare type of galaxy merger. Astronomers say that the symmetry of the resulting cosmic owl is a strong indicator of a head-on collision between two galaxies of similar mass. Both of the ring galaxies that make up the cosmic owl are relatively small, each measuring in at only about a quarter of the diameter of the Milky Way. At the time of the collision, each of the owl's eyes represented a galactic core of densely packed old stars surrounding a black hole. Where these eye-like galaxy edges began to merge some 38 million years ago, we get to the area known as the beak. This is a place of active collision, packed with molecular gas, the fuel for star formation. This ancient collision may have been the very catalyst that sent RBH1 on its rapid escape path. There are two leading explanations for what could have happened to RBH1. Either a merger of two black holes, or a three-body interaction with a third black hole involved. So, which is it? When ring galaxies like these collide, their supermassive black holes spiral nearer and nearer to each other, drawn together by their massive gravity. When the observation was initially revealed in 2023, before it had been confirmed by the Webb, the leading explanation seemed like it could be the three-body gravitational interaction scenario, where three supermassive black holes were brought close enough to interact with each other through the galactic merger. In this case, the two supermassive black holes at the galactic cores of the merging galaxies spiral together to form a binary black hole system at the center. This kind of binary black hole system can last billions of years, and if a third supermassive black hole gets close enough to the galactic core, this three-body interaction can send one of them flying out of the core with enough velocity to escape the galaxy altogether. But with more accurate measurements, it became clear that the better fitting scenario was actually a black hole merger. The mass was the smoking gun in the mystery. If it had been 3 black holes interacting, the lowest mass black hole would be the most likely one to be shot out of the system, whereas in a merger, the larger, combined black hole is the one that would be ejected. In this case, the supermassive black hole's mass was calculated to be greater than 10 million times the mass of our Sun, too massive to be a small third black hole, but just what would be expected from a binary merger and gravitational kick. As the 2 ring galaxies of the cosmic owl collided, the supermassive black holes at their respective galactic cores merged to form one new supermassive black hole. The asymmetrical release of gravitational waves from their merger would have caused such a violent recoil that it would easily be enough to suddenly send the new black hole flying out of the host galaxy. Models of this scenario are consistent with measurements of RBH1's velocity and the mass of the galaxy it left behind. In other words, this theory is consistent with what we've measured and simulated. If the team is correct, the ring galaxy's central black holes would have merged into one supermassive black hole that was flung out of the cosmic owl by the gravitational wave recoil. In a merger like this, the galaxy system may be temporarily left with no central black hole, although we don't have concrete evidence one way or the other just yet. Whilst this remains a mystery, we do at least know that this unusual galactic merger sent a supermassive black hole on a race toward intergalactic space. The confirmation of RBH1 marks a new era in our understanding of how supermassive black holes, galaxy mergers, and intergalactic star formation can relate to each other. This is the first clear observational confirmation that supermassive black holes can be slingshot out of their host galaxies, and it has revealed the stunning side effect of leaving a string of young stars in its wake. Before the observation, simulations had predicted the wake of a runaway black hole might glow, but few expected them to become stellar nurseries. Even more excitingly, if a runaway supermassive black hole can happen once, it can happen again. After all, galaxy mergers are common and happen often over the lifetime of a galaxy, so black hole binaries should happen regularly, laying the way for black hole mergers or 3-body interactions. For a long time, we've seen black holes as permanent fixtures within their host galaxies, but now it seems this is certainly not the case. Even before this confirmed event, astronomers had spent years gathering evidence of other runaway supermassive black hole candidates, and we think we found multiple instances of wandering black holes, like this spiral galaxy, the memorably named J04372456, located around 288 million light-years from Earth. It's about 3 million times the mass of our Sun and seems to be moving at a significantly different velocity compared to the rest of its host galaxy. In another case, the central galaxy in a cluster known as Able 2261 should have one of the biggest supermassive black holes in the entire universe, between 3 and 100 billion times the mass of our Sun. And yet, it seems to be missing without a trace. A team of astronomers are investigating the hypothesis that, similar to with RBH1, this black hole may have been kicked out of its host galaxy due to gravitational recoil. These curious cases confront researchers with even more questions. How often are supermassive black holes flung from their galaxies, and how many wandering or runaway black holes are out there, zooming through intergalactic space? Despite other candidate runaways, RBH1 is, for now at least, still the only one we've been able to confirm, and it was difficult to spot, just a thin, faint, faraway signature. That could be about to change with the Euclid mission and the Nancy Grace Roman Space Telescope's wide scans of the sky in Hubble-like clarity, and with the introduction of machine learning tools to help spot these long streaks, we may go from just one confirmed case to an entire population of known runaway supermassive black holes. For now, one thing is for certain, galaxy collisions may last for billions of years, but they are anything but slow or peaceful events. Marked by chaotic collisions and violent forces, they are capable of launching entire supermassive black holes on a runaway path across intergalactic space. How odd and beautiful it is that these destructive scars across space are the very reason that millions of new stars are capable of being born in their wake. I'm happy to announce we have a weekly newsletter to keep up with all the discoveries in our cosmos, and our designer Peter has made the most beautiful email you'll ever receive. Sign up with the link down below. It's the best way to stay connected between videos. Short, focused updates on what's new and fascinating in space each week. No spam, no filler, just the good stuff. You'll get the latest news, visuals, and insights delivered straight into your inbox. If you enjoy Astrum videos, you'll love this. Join the newsletter and stay curious with us.